welcome back to the continuation of our TensorFlow 2.0 Computer Vision Code book. I recommend we get this book, very illustrative. So today we'll look at chapter 2, which is performing image classification, and there is a particular project that we'll be looking at, which is to detect smiles in data. So I've started the code by git cloning the dataset, and we have the dataset here already git cloned, and then we import all the necessary packages. So these are the necessary packages that needs to be imported. Then we define a function to help us load the image and the labels, and that is that function which we've already run here. Then we have our network. We're used to building a network. So we build a network this way. Then the next thing is for us to load the image pattern. I did a bit tweaking here because in my own case I have some stuff that's a bit different. I'm not loading it into .keras dataset, and my downloaded version does not have the master, as you can see here. So I took this, I removed this once and started with a smart D, and as you can see in here, so I have this, then I have this. Now, so I have this, the rest is just the same, asterisk, then asterisk.jpg. Then this is something I wanted us to see in here in the loading image. This one actually pick the second to the last directory. As you can see here, this one I wanted to run. So if you look in here, you will see if you're going like this. So here you have negatives and positives. So here, so this is the last directory that you have before you start seeing the images. So this will be -1, this is -2. So this is this part here. This guy here returns that particular folder. So in this case, it will return these negatives, and in the next line you check, is there positive in that label? If it is not, then it's going to return false. So that's why this will be printed as false, and by the time you cast it to a float, everything that is false will be converted to 0. Okay, but when you get in here, this is the second to the last positive. So we have positive and positives. That's 1. So that will give us a true. By you cast it to a float, the true will be casted to label 1. I hope that would make sense to you. So if you come in here, I'm just running this so that you could see. So you see that the label is false in the first instance. Then after it has been casted, it becomes 0.0. And after the negatives are done passing, and we start getting the positives, you will see that the label first is true, and after the casting it becomes 1.0. So just a little bit of tweak here. So you just did that pattern here. So I'm going to now see, that gave me some tough time to be able to find out. So instead of loading just for us to see, I can just then still do that into our folder X and Y. Okay, so our X is the train and our Y is the label. So for us to be able to see the total length of the data set, so you get in total. If you want to get the total of the positive, just to sum up the Y, and summing up the Y, we just sum up all the ones, and since all the ones are positive, so just a way of using the sum in NumPy to get how many ones are there, and that corresponds to the total number of positives that are there, and we can get the negatives by that subtraction. So we do that normalization, and then we can easily get the total positives and the total negatives there. So there's something interesting I want us to see in here. You will see this is the total negative. So the total negative is 9475, and the total positive, it's 3690. So this is like 3 times. This ratio is like ratio 1 to 3 if you want to look at it. So if you divide the total negative by total positive, so we'll be getting an imbalance ratio of roughly 1 to 3. I publish a paper on imbalance ratio. You may want to take a look at it on class imbalance, and in that paper we look at the how to address class imbalance using an unsupervised approach. So in class imbalance, you have different ratios, and they often affect the performance. So you want to take a look at that. Okay, so we can continue now to look at how we can solve the problem of this imbalance. But first of all, let's continue to do the processing of our data. These are pretty straightforward. We use the train test split from the skland pre-processing. You will see that we imported that from skland skland model selection. Okay, so train test split, skland model selection. So we import that from there, and we can use that to get 80% of our training data as train, and we use 20% for testing. Okay, I don't know what this stratify equals to is. I don't know if anybody knows Google, but the random state, I think that should be for seat, so that we can get the same result as the got. Then we further now split again the training set. We further split the training set, so we have 80-20. So out of the 80 again, we have 80% of 80 as our train, and 20% of the 80 as our validation. Okay, so we have the random state as well, so we could get the same result. So essentially what this line of code is, we're getting the training, the validation, and the test data sorted out there. So we can just have that line of code, and we run that. So we can build our network, and pretty what we're already used to. So I will quickly go over this one. So we build our network, and we can compile. Then we specify the number of epochs, the batch size, and this is where the interesting come into place, which is where we have the class width, and that is where we're going to spend some time and look at what is the impact of that. So what I'm going to do is that we're going to have two network. We're actually going to train two networks. So instead of just training this network, we're going to train one network without the class weight, and we train another network with the class weight. So I can just say model.fit. So this one, first let's train the network without the class weight. So let's remove this class weighting, and let's see what the result is going to be compared to when we do the class weight. Okay, I would like to do some plotting. So let's see the model history. Let's just say history. Store it in history. We say model underscore 1. So we just store that, and let's train for the 20 epochs. Yeah, let's train for the 20 epochs and see what we have. So we're training now, and it's without the class weighting. Now I want us to see more information about the class weighting. Here it says that train the model because the data set is unbalanced. We are assigning weight to each class proportional to the number of positive and negative images in the data set. So in the class of 1.0, which is the positive class, we are assigning the weight of total divided by total positive, and the class of negative, we assign the weight of total divided by total negative. So, but I would like us to see what's the impact of that in training. But then while that is training, let's say model.fit, and we can see what happens in our model.fit. Let's look at the documentation of model.fit, and we look at what the model and fit in the TensorFlow. So in TensorFlow we have model.fit, so you will see what the fit takes, the fit function in the model. You should be able to see the fit function in there. Where's fit? Okay, this compile, this evaluate. Let's see what the fit is. So this is the fit, and this is the class weight we're talking about here. So in the first, the one that we're training now, the class weight is none. Okay, so let's see what the class weight property, what does it do? So this is optional dictionary mapping class indices as the integer to a weight float value. So it's used for weighting the loss function during training only. So this can be useful to tell the model to pay attention to samples from an underrepresented class. Okay, so we're training that now without telling the model anything, but we'll also train again and see what is the result when we actually now tell the model to pay attention to that. So I will redeclare the network again so that I can run the other part. So we have again model. So I will declare the network again. So what I will now do here is I will call the network with weighting, model with class weighting. This is class weighting. So we're weighting the class here, then we can still compile it with class weight. Okay, so now when we're now training here, so we can now say our second model 2, model history 2, we can say it is model with class weight underscore with class weight, and we can use that to get. So we're going to have two models trained. Yeah, so let's build this network. So building this network now, then we have let me see what we use here, history underscore model underscore 1. So this one should be history underscore model underscore 2. It is a model 2. Okay, so we'll run this as well, and that will take some time. Then we will now plot the two models, and we can see how it's going to what is the performance of the class waiting on the training. So we can see that performance by evaluation, but I will want us to see what really happens in the training. So I want to plot this uh, history underscore model. So we can go back to our chapter 1 and get some code there that we use to plot the history. So let's go there and see how we can actually plot the history. To make it fast, I can just search history here, and that will take me to that. Okay, so that is the history. So I just need this function, and do I have a metric? Yeah. So I need this function, so I can just copy this function in here, and I can use this function to do plotting the model history. And once we do that, that should give us something like this. So we should be able to see something like this. So we can plot the model this way, the two models. So I'm going to plot the two models. So I'm going to first of all, so define this function, and what is the metric that we're using in the current one. So let's go back to chapter 2 now and see the metric that we're using to train our model. I guess that's accuracy. Okay, so we're using accuracy as the metric. Of course, the history returns both the loss and the accuracy, so we should have access to the two, right? Yeah. It should return both for the the loss and the accuracy. So this will give us for both of them. So this should be able to plot this. We don't know what is the range of the loss, so well, I don't know what it could be. Maybe it's 2.0, but we can rerun that if it is not. The range of the loss is not within that. We can also see it. Alright, so model history model 1. So this is the history model 1 underscore 1, then history underscore model 1 here. So we can see that here. And for the others, for the second one, underscore 2, and this one 2, underscore 2. Okay, so we can plot both the accuracy and we can plot for the other one. So I would love us to see what the training looks like. So this should show us both the validation and it shows us both the validation and validation loss and validation accuracy. Yeah, so when we send that to it, so the loss and the accuracy, so this is for the loss, so it shows us the model validation, and it shows the loss, the validation loss, and the train loss. And this one too, it shows accuracy. I don't know why they label that as. I would have preferred they just label the validation loss. Let me see where they did that. There's another thing we need here. Plotter the history plotter. We've not looked at that. My running time issue here. So there is plot.history plotter. So let's look at that history plotter here. So this is the history plotter. So we need this guy to be imported. So let's see where we got it from. The history plotter. Control C, Control V. So where is it? I think we imported. We import this tf.doc. Oh, that should be that. The first one is done. Oh, that's pretty fast. So that's the tf.docs. Yeah. Right. So if there's any issue, we can always see where that. Yes, so we needed to import this guy. So we didn't import this. We might run into an issue here. That's it. So we have to, we're supposed to import this guy. Then we return this guy, we return this guy, we return this guy. Okay, so we come back when it is done, and we will see what our result is like. Okay, thank you for listening, and see you when the program finish running so that we can wrap up that aspect. Thank you.